Guys, today we're going to talk about common logs and natural logs, and I'll show you how to evaluate both of those. I'll show you how to solve equations that involve both of those, including some shortcuts in solving those equations, and we'll also do a couple of application problems. So a common log is just a log base 10. So a lot of times it's written without a base. So here's log base 10 of x. This is the exact same thing, log x with no base. That means the base is 10. And that was made to fit our base 10 system. There's also natural log, which is a log base e. E is a number. It's an irrational number, just like pi is. E is that number right there. There is an E button on a scientific or a graphing calculator. Okay, so log base e is the same as natural log. So log base e of x is the same as natural log x. So we're going to evaluate some logarithms and some natural logs. A common log, the calculator will do for us very easily. We just have to type in log 34.95. And it will know that it's evaluating the common log, or the log base 10. And we're asked for 4 decimal places here, so that's 1.5434. Okay, another common log, log negative 2.6. And I get a non-real answer. Because I can't raise 10 to some power to get a negative number. So there is no real solution to this. Okay, so my domain here would be all positive numbers. For this input here, I cannot put in a negative. I can't have a positive, I can't have a real number base and have a positive argument. Okay, this next one I'm going to put into log form. 10 to the y equals 27.3 is the same as log with a base 10 with an argument of 27.3 and an exponent of y. So that's the same as log 27.3. So log base 10 is the same as just log 27.3. We get 1.4362. Next is natural log 63. So natural log, we need to find ln on the calculator, which is right under log. Natural log 63. 4.1431. Number 5 here, I'm going to change to log form. I've got a base of e, argument 14.2, and an exponent of y. So log base e is natural log. So natural log 14.2 equals y. Natural log 14.2, 2.6532. And the last one here, natural log x equals 5. So that natural log x equals 5, I'm going to write in log form, just regular log, that's log base e of x equals 5. Now I'm going to put it into exponent form. The base is e, the exponent is 5, the argument is x. e to the 5th power equals x. On my calculator, there's an e that is a second function with division. So second and divide gives me an e, and I can raise that to the 5th power. So we get 148.4132. Some properties of logarithms. Log base b of b to the x. So what power raises b to make b to the x? The x power. This is a common log, so it's base 10. What power raises 10 to make 10 to the x? The x power. Natural log is log base e. What power raises e to make e to the x? The x power. So log base b and then a base b here gives me that exponent. Log base 10 and a base of 10 here gives me that exponent. Natural log and an e gives me that exponent. Next is a raised to the power of log base 4 of x. So a raised to whatever power raises a to make x. It is x. So a and log a as a power will cancel. This one's just the same except it's a 10 with a base 10. So it's 10 raised to the power that raises 10 to make x. E raised to the power that raises e to make x. We're going to use some of those properties to solve these equations using some shortcuts. So log x, which means log base 10 of x, so that's a base 10 there, equals 0.8654. If I change both of these into powers with a base of 10, what happens is that cancels. So x equals 10 to that power. So 10 raised to 0.8654. $7.3350. So I've got a 4, 9, and that 9 after bumps that 9 up to a 10. So it turns that 49 into a 50. Okay? Here, natural log of e to the 8th. What happens is those cancel and I'm left with just that power, like right here. Natural log of e to the x is x. Natural log of e to the 8th is 8. Natural log is log base e. So if I put a base e on both sides and raise to that power, x equals e to that power. So e raised to negative 1.7395. 0.1756. If I expand this one, because I've got a 10 to the x, if I turn that into common log or log base 10 of 10 to the x, and do that to the other side, log 36, log base 10 of 10 to the x is x. And I can evaluate log 36. This one, I want to get that e to the x by itself first, so I'm going to divide both sides by 7 and get 6 equals e to the x. And just like I did here with the log base 10, I can do a log base e, or a natural log. And natural log and e will cancel. So I do natural log 6. 1.7918. Okay, and my last one here. If I get one natural log per side, I think this is going to be easier. So I'm going to move that over. So I get 3.2 minus natural log 4 equals natural log x. Now, if I just want to make this side x, I can do base e on both sides. And in my calculator, I can type in e raised to the 3.2 minus natural log 4. .1331. So money invested and compounded monthly grows by this formula. So that's A equals P times 1 plus R over N to the N times T power. A is the ending amount, so the amount of money we have in the end. P, principal, the initial amount of money we invest. R is the interest rate. N is the number of times that it's compounded per year. T is the time in years. You want to have $100,000 at age 50. You invest at 7%, compounded monthly. How much should you invest on your 20th birthday? Okay, so we've got the variables A, P, R, N, and T. A is the ending amount. We want to have $100,000. P is the principal or the initial amount. That's what we want to find out. The rate is 7%, 0.07. N, the number of times compounded per year. It's compounded monthly. That's 12 times per year. And T, you're going to end on your 50th birthday and start on your 20th. So T is 30 years. So 100,000 equals P times 1 plus 0.07 over 12 to the 12 times 30 power. Okay, so to get P by itself, I can actually do this in one step. I need to divide by all of this. 1 plus 0.07 over 12 to the 12 times 30 power. Let's simplify that. 12 times 30 is 360. And since I divided, that's canceled. So 100,000 divided by 1 plus 0.07 divided by 12 raised to the 360 power. I need to invest $12,320.59. The number of bacteria grows according to B equals B sub 0 times E to the RT power. B sub 0 is the initial amount, B is the ending amount, R is the rate of growth, and T is time in hours. If there were 400 bacteria at time 0 and 700 at 3 hours, what is the rate of growth? So we've got B sub 0, B, R, and T. So B sub 0, the initial amount is 400 bacteria. B, the ending amount, is 700 bacteria. The rate is what's in question, and the time is 3 hours. So 700 equals 400 times E, which is a constant, that is a number, not a variable, to the RT, so R times 3 power. So the first thing is to divide by 400. And that's going to simplify to 7/4 equals E to the 3R power. To get that 3R out of the exponent, I could do a natural log on both sides. So natural log 7/4 equals natural log E to the 3R power. So I get natural log 7/4 equals 3R. And then I can divide both sides by 3. So natural log 7/4 divided by 3. So I get 0.1865, which is 18.65% is my rate of growth. So how many bacteria will there be at 12 hours? The starting amount is still 400. The ending amount will change because now we'll be at 12 hours. The rate is 0.1865, and the time will now be 12 hours. So B equals 400 times E to the 12 times 0.1865 power. And that I can type in all in one step. So I've got 400 times E raised to the 12 times 0.1865 power. So in the end, there will be 3,749.8 is not yet a whole bacteria, so we'll go with 3,749 bacteria.